Welcome back to class. We've been looking at elliptic curves, and in our last lesson, we looked at how to find the order of a point on the elliptic curve. Not the order of the elliptic curve, but the order of a point. That's what we looked at last time. So today, now I want to look at how do you find generators of the elliptic curve? That is, how do you identify a point that can generate all the other elements on the elliptic curve? That's what we want to look at today. How do you find a generator? A generator is an element that can generate all the other elements. Is that okay? Yes. So, and we say that, of course, we said the elliptic curve, the elements on the elliptic curve, together with the identity elements, form an abelian group and addition. They form an abelian group and addition. So that means what we want to add that element itself several number of times until we get the identity element. Every time we are adding it to itself, it's generating another element of the group. Is that okay? Every time we add it to itself, it's generating another element of the group. So I've defined a generator here, and I've said the generator G on the elliptic curve, and this is the initial of the elliptic curve, where we're looking at mod Q. Mod Q. F is the field, mod Q. So it's a point such that every other point of the curve can be expressed in terms of G. Every other point on the curve can be expressed in terms of G. So what that means, therefore, supposing I'm given this point, G. So G itself is a point on the curve. Is that okay? Now I'll then get 2G. 2G will give me another point on the curve. 3G will give me another point on the curve. 4G will give me another point on the curve. So I do until I get the identity element. Now, if I'll have obtained all the elements of the curve, if I'll have obtained all the elements of the curve, then I say G is a generator. By the time I reach the identity element, if I'll have obtained all the elements of the curve, then I would say that G is a generator. Otherwise, it's not. So that's what we want to do. So in this equation here, K is just the scalar, could be 1, 2, 3, 4, and so on. And we are doing that until we get the identity element. We are doing that until we get the identity element. Now, so when do we say that G is a generator? Therefore, we say that G is a generator if the order of G is the same as the order of the curve. The order of the curve, we mean the number of elements on the curve. Is that okay? That's what we mean by the order of the curve. So if G has the same order as the order of the curve, then we say that G is a generator. That's what we mean therefore. In other words, it can generate every element of the curve. So I'll take an example before we go to look at how do we then write a code that will give us the generators. Before we look at how do we write a code that will give us generators. This is the example. So our elliptic curve is here. We are doing it over F5. And of course, last time we looked at a theorem that tells us the number of elements to expect here. Now, so the number of the elements that I expect here are these are the elements. I don't know whether this is 5 or 7. We'll see. I don't know whether I wrote the correct thing. How many elements are this? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Just check. Let me check if I was using 7 or 5, first of all. I was using 7. Yeah, this is supposed to be 7. Because I'm seeing the elements here, very many. These are 10 elements. That is far from what we expect. Because what we expect is the number of elements of this curve. Then, if this would be 5, then there are supposed to be 6. Or if they were to go far from 6, then it will be plus 2, the square root of 5. And this does not look like it can go up to, yeah, it can go up to 10, but I was using 7, not 5. So this is supposed to be over F7. Now, so, oh, of course it's here. I've used it correctly here. Now, so you can get the number of the points on the curve using the code. So we looked at the code that can generate the points on the elliptic curve. We had that code. So what we are interested in is what element, or the question is point G, which is 3, 1, a generator to this curve? That is my question. Is point G, which is 3, 1, a generator? So I just want to see whether point 3, 1 can generate all these points. And if it does, then we say it's a generator. But if it cannot, then it's not a generator. So it must generate these 10 points for it to be called a generator. So that's what we mean. So then I begin my finding out whether it's a generator. So I just want to add a G to itself, so I'm using P instead of G. It's supposed to be G, because I called it G31. So I then add G to itself a number of times, and I want to see if every time I add it, I get another element of the group. So when I add it once, just one G, I already have one element of the group. Then when I add it to itself, I get another element of the group. Add it 3 times, I get another element of the group. So when I did all this, I discovered that 3, 1 was to generated all the elements of the group. Therefore, it is a generator. Now, so this one here, at this point, there's no working. At this point, there's working because we are adding a point to itself. We are adding a point to itself. And we know the formula that first of all, if it's the same point, we first of all have to get gradient. And this gradient will be given by 3x squared plus a out of 2y. That is how you get the gradient of this curve. Is that okay? Yes, that's how you get the gradient. And we know how we came up with this equation from the equation of the elliptic curve, which is given by y squared is x cubed plus ax plus b. We use implicit differentiation to come to this. So when you use implicit differentiation, this is what you get. Now, so after getting this s, you now want to get the point, the x value for the sum. The x value for the sum, and is given by, that is our slope square, then minus x1 minus x1. Is that okay? Is it? Yes. And then what about y? The y coordinates will be given by that slope into x1 minus x3, then minus y1. So that was our formula. So that's the formula then you are using to get this. So it means when you're writing your code, one, you have this equation to get the slope. Then you have this equation to get x3, and you have this equation to get y3 in places where you'll be doubling. In places where you'll be doubling a point. Now, once you've gotten 2y, 2p, you now want to get 3p, and this is same as 2p plus p. These are two different points. These are two different points. You've obtained 2p from here, because once you calculated this, you have your 2p as x3, y3. So in this case, it happens to be 5, 3. Now, once you have 2p, you now add to it p. These are two different points. Then we come up with other formula now to add two different points. First of all, the gradient given by change in y over change in x. Change in y over change in x. That's a good gradient. Then after that, get now the x3 value as this gradient square minus x1 minus x2. And then what about y3 value? Would be s into x1 minus x3, then minus y1. So that then gives you the coordinate for 3p. So that means, again, you must have a formula now, getting gradient when 2 points are different. Then after getting that gradient, you then get the x coordinate and the y coordinate for the sum. So those are the two formulas we require. So our code should then have that function for summation, for adding points. So that function, one of the work it will be doing is to find the gradient if 2 points are different, and then find the gradient in the 1 point. Then after that, another work it will be doing is to find the x coordinate and the y coordinate for the summation. Now, that is not the only function we require in our code. The other function that we require in our code is one that will be doing the inverse of the denominator. The inverse of the denominator. So we require the inverse of the denominator. Because what we then do to get s, you see, you cannot just take this numerator and divide by the denominator. The way we do it is you take the numerator, 3x squared plus a, then multiply by the inverse of the denominator. That's how you get s. Don't just divide. In modular arithmetic, you cannot do that. You have to multiply by the inverse of the denominator. So we require a function that will be doing the inverses of the denominator. And of course, getting the inverse of the denominator, we already know how to do that by using the extended Euclidean algorithm. Now, those are not the only functions that we require. We also require a function that will assist us to detect if the point given to us is at infinity. So in that case, then it means we don't need to use any formula. Good, so that's what we're supposed to do. So then let's look at the code. Just before that, I stated here why generators are important, and this you just go through them. In the protocols like elliptic curve, the Diffie-Hellman protocol. We shall require the generators. In digital signatures, we shall require generators, and also in group operations. And so to find a generator, again, I've said, you first of all compute the order of the elliptic curve using any algorithm that we have. So once you have the algorithm that gives you the order, like I've given you the example of this, this one is an algorithm that is applied in a real life situation. Then you would then test if that point, if the point that you want to see whether it's a generator, whether it generates all the elements of the group, you then want to see. So first of all, you have an algorithm that gives you the points, the order of the group and the points. Then you now want to see whether that point generates the points you have from one above. I've already explained this, just the same thing. Now, we already explained about security on elliptic curves. In our last lesson, we said that to ensure security in elliptic curves, the points that you're using should be points of higher order. So you're looking at the order of the point. It must be very high so that your things remain secure. Now we can apply it in zero knowledge proofs. You can also apply it in post-quantum cryptography. Of course, we know that currently post-quantum cryptography, a lot of research on post-quantum cryptography is about lattices. And we also have research on elliptic curves in post-quantum cryptography. It's not just about lattices. We also have research about the elliptic curves to ensure post-quantum secure, that data is post-quantum secure. So when you are talking about post-quantum cryptography, then there are very many things, and you cannot exclude, you cannot leave out the elliptic curves. Now, so the code is here. This is my code for doing the generator. Now, this code, the way I've put it, first of all, I want it to give me all the points of the elliptic curve. After giving me all the points on the elliptic curve, I also want it to give me the order of each. The order of each. Then after that, it does what I want. Then it selects those points that have the same order as the order of the group as the generators. So that is what it will be doing. So one, it will generate all the points, generate all the points. And then two, determine the order of each of the points. Determine the order of each of the points. Now, supposing my graph is of order 10, it has to determine the order of each point. Then after doing that, it then selects those points that have order 10. And those are the ones it gives me as the generators. So that is what this code will be doing. Of course, you can customize it and make it shorter so that it does not have to go through all those steps. You make your steps shorter. Now, so what does this part do? This part is just defining a point. It's defining a point on the elliptic curve. And this infinity is to tell us whether the point is at infinity, is a point at infinity. That is what it's telling us. So this will be telling us to the defining point xy, or if the point is at infinity, then it's also telling us that. Now, so is this function is at infinity. So this, while this was just defining the point, it was defining the point, but this one is determining if that point is at infinity. That's what it's determining. So it determines if the point is at infinity. If the point is not at infinity, then we can now proceed and do some summation. Now I say the code should have the function for doing inverses, performing inverses in the denominators. Our denominators, of course, will require the inverses. Now, this is done by the extended Euclidean algorithm. But how do you start? You start by letting t be mutable, and initially put it at 0. So initially t is taken to be 0, but it's mutable to be changing from time to time. T is supposed to be the inverse. T is supposed to be there. So T stands for the inverse. And then we have new T. We have new T. New T, you make it to be 1. Initially, but again, this is mutable. Then we have R for the remainder. R for the remainder. Remember, this is the Euclidean algorithm, so we have the remainder. So again, it's mutable. And initially, it's M. M is our P. Is that okay? Is our, we see we're doing it mod P, so that P is our M. So in this case, our M is 7. In this case, our M is 7. In this case, our R is 7, because our graph is mod 7. And then what about new R? New R is also mutable, and we make it the remainder of A on division by 7. The remainder of A on division by 7. Now, so what was our N in this case? Because I want us to use a real example so that you understand what it is. In this case, our A is 4. Our A is 4. So the remainder of A on division by 7 is still 4. It's still 4. 4 divided by 7. The remainder is 4. So again, in this, our new R is 4. Now, so what is happening here? What is happening here is that after setting those initials, you enter a loop and you remain inside this loop until the remainder, the new R is 0. So that's what it's saying. While the new remainder is not equal to 0, you remain inside the loop and perform what is there. While it's not equal to 0. But once it gets to 0, you now exit the loop. Now, so let's just look at this example, therefore. How is it working? How is it working? We want to get the inverse of 4, for instance, just taking an example. Of course, it's not only 4. We are saying that A will be, for instance, we are getting the inverse of what is in the denominator. I'm just using 4 in this case. But what will be in the denominator is our A. What in our denominator is our A, and we want to get its inverse. So suppose we want to get the inverse of 4 mod 7, therefore, I enter the loop because our new R is 4, is not equal to 0. I enter the loop, and inside the loop, the first thing I do, I get the quotient. And the quotient says that R divided by new R. So our R is 7 and mu R is 4. So when you divide, of course, you just take what is the whole number. You take the whole number there. Now, so after you've gotten this quotient, you proceed and get T. You update T and also update new T. So what does T become? T becomes the original T divided by the quotient. This quotient, but the quotient has to be multiplied by the new T. In this case, our new T is 1. But it is mutable, to be changing. So once we are done with this process, this T that we've just obtained becomes the new T because there's swapping. There's swapping here. We obtain the new T. What we obtain is the new T. And what was the new T now becomes T. Becomes T. So that's what is happening. So once you obtain this new T, you come and update your R, your new R. And you can see it's reducing. It has to reduce until it becomes 0. R has to reduce. The new R has to reduce until it becomes 0. What was the new R? Our new R was 4 in this example. The remainder of M division by M. So now take that 4, subtract the quotient, multiplied by new R. So it has to reduce. Our new R has to reduce. So while it's not 0, you again repeat the same process. Again repeat the same process until it becomes 0. If it gets to 0, you exit the process. You exit this loop. Now, look what the statement coming just after that. That if T is less than 0, that after the process you obtain that your T is negative. Here, if you obtain that after the process, when you're exiting the loop, your T is negative at that point. If it's negative, then you have to add M to it to get a positive T, get a positive value of T. That's what this one is saying. That a T therefore becomes the original T plus M. That's what this symbol means. That is if it's positive. If it's negative. Now, so this function therefore was to get the inverses. But then we have the function for adding. Elliptic add. Elliptic add. We are adding P and Q. Now, this, before it does the summation, it calls on this function is at infinity and is asking this function to tell it whether P is a point at infinity. So he's saying, he's asking for this function to tell it whether this point is at infinity. Where's this function? This function was above here. This function was above here, and we said that this function, its role was to determine if the point is at infinity. So then when it's asked whether P is a point at infinity, it's supposed to respond to that. Now, if the answer is true, if the answer is that it's true that P is a point at infinity, and we wanted to add P plus Q, it has been discovered that P is a point at infinity, then it means that the result is Q. That's what it says, return Q. Return Q. If P is a point at infinity, then we return Q as the result. In a similar way, it asks if Q is a point at infinity. And if it's true that P is a point at infinity, then it means that this will give us P. So return P in that case. So you return P because P, a point at infinity, we said, is the same as the identity elements. When you add it to something, there's no change. When you add identity to P, just get a P. Now, so supposing, therefore, that none of them is a point at infinity, then it proceeds and it wants to do calculation for summation this time. But it begins by saying that if the x value of P equals the x value of Q, if the x value of P equals the x value of Q, so supposing this is P, and then we have Q, and the x value again is the same. And the y value of P is not equal to y value of Q. So a case like this, where the y values are not equal, but the x values are equal, then the result will be a point at infinity. The result will be a point at infinity. So there's no need of calculating gradient for these points. The result is known. And we say that these points, of course, they lie on the same vertical line. So when they lie on the same vertical line, there must be inverses of each other. They must be inverses of each other. Is that okay? Yes. So since they are on the same line and they're inverses of each other, when you add points which are inverses of each other, what you get is identity elements. So they're inverse of each other. So in this case, this is supposed to be 3. It's supposed to be 3. If they're inverse of each other, it's supposed to be 3. So that the sum will give us 7. Now, so if they lie on the same vertical line, this is what this is saying. That if the x value is equal, then the sum of those 2 points will be infinity. Will be a point at infinity. So that is what this code is doing. First of all, it's identifying if one of the points is a point at infinity, and then it returns the other point. It returns the other point. If one of the points is a point at infinity, it returns the other point. Now, if the x values are equal, then it returns the infinity. Now, if these are not the cases, then it means, one, supposing we have this point P, and this is point Q, where you have x value of P and y value of P, x value of Q and y value of Q. If this is the case, then we proceed and find the gradient. Proceed and find the gradient, and this is why it's find the gradient. So it's saying, supposing this x1 and this x2 are equal, and y1 and y2 are also equal. So it means P is the same as Q, is the same point. Is that okay? If x values are equal and y values are equal, then that's the same point. Is it? Yes. So it says, if that is the case, if it's the same point, then determine the gradient using this formula. Determine the gradient using this formula. Just saying that if it's the same point, determine the gradient by 3 multiplied by x squared plus a. We normally have divided by 2y, but instead of 2y, we multiply by the inverse of 2y. The inverse of 2y. Multiply by the inverse of 2y. And then the result, reduce it mod m. That gives you the gradient for that curve. That's how you get the gradient to that curve. That is, if it's the same point. Else, that means the points are not the same, they are not equal. Else is referring to this condition. Is referring to this condition. Is now talking about a case where x1, a case where the 2 points are not the same. Now referring to a case where the 2 points are not the same. So it says else, if the 2 points are not the same, then you find the gradient change in y over change in x. But instead of over change in x, let's multiply by the inverse of change in x. Multiply by the inverse of change in x, then reduce mod m. Now, whatever answer you get gives you the third point that you require. So it gives you x3 and y3. So that x3 then is obtained using the same formula, lambda square minus x1 minus x2. And the answer is reduced to mod m. And y3 is calculated by lambda, where lambda is the gradient, times x1 minus x3. Then the result, you subtract y1 from it and reduce mod m. Reduce the result mod m. Good, that is how it does the calculations for summation. So is it summing point P and point Q? So there are various scenarios there. There are various scenarios. If the point is a point at infinity, one of the points is at infinity, and another one is not, or the point is the same, or the points are equal, are different. Those are different scenarios. Now, after that, it now comes and computes scalar multiplication. Scalar multiplication. So it wants to multiply point P by 1, by 2, by 3, by 4. And what it's doing, it wants to see whether this point would then generate all the other points. Is that okay? Just the same way we're doing. Wants to see whether this point is a generator. Whether it's a generator. So it's multiplied by scalars. So it begins by P multiplied by 1, P multiplied by 2, P multiplied by 3. It begins by this. Let the result be infinity. So supposing you want to get n of P, it begins by calling this as infinity, point at infinity. That's why it begins. And then it says this is mutable, to be changing with time. Then it begins multiplying. And it will do that until it reaches n. N times. N, so it does 1, 2, 3 up to n. So if n was 6, it does up to 6. So n is 6. So that is what this curve, what this function would then be doing. Now, this one does not have much. It's just is a point on the curve. The function is a point on the curve. So this function is just to verify if the point you are dealing with is on the curve. Of course, before you add a plus b on curve, on certain curve, those 2 points must first of all be on the curve. Is that okay? So it doesn't want to be adding 2 points that are not on that curve. So how does it determine? We have the equation of the curve, x cubed plus ax plus b. So what it does, it has point, let me say 3, 4. It has 0.34. It takes this 4, this is our y value, puts there. And let me say we are doing it mod 7 in this case. So it substitutes y value there. That will be 16 mod 7, that gives you 2. Is that okay? Then substitutes the x value here, substitute the x value here, and then again reduces mod 7 to see whether the result on the left side is the same as the result on the right side. If the two are equal, then it means this point, therefore, is on the curve. So that is how it determines, by just substituting the y value and then the x values, and then comparing the result on the right with that on the left. Any question after that? Any question? Okay. Now, so after multiplying, at this point, we're just multiplying those that point by scalars, and getting results. But then after that, this is now where it goes to the results above, to identify points which are scalar, which are generators. That's what it's saying. Find all points. It's calling on this function. Find all points. This function is here. Find all points. So it's calling on that. So it's going, this one was finding all points by multiplying scalars by a point. So you have 3, 1, multiplied by 1, 3, 1, multiplied by 2, and see what you get, And then 3, 1, multiplied by 3, and see what you get. And then after that, this one goes there and asks it to find from here, to want to tell whether that points are generator from this function. It's able to tell whether it's a generator or not. So that's what this function is doing, just finding whether points are generator, but it's not the one doing it. It's calling on the other functions to give it the results they obtained. Now, then we have the main function. Of the main function, of course, I've included notes on that explain how the code works, and you look at it later. Look what this, I've explained all of them, how the code is working, a function, what each function is doing, and so on. Okay, so let me share now the code. We'll see how it runs. So this is the code. So it's the same code that we've already explained how it's working. So this is our main function. And I will input our parameters. I will input A, B, and M. So when I run, it gives me, first of all, it begins by giving me all the points of the curve. When you are doing your code, you can omit this part. For me, I asked it to give me all the points first of all, because I wanted to be sure that it's giving the right points for the curve. I wanted to ensure that it give me the right points. That's why I asked for all the points. And of course, again, that was to tell me about the order. I was to count those points and know what the order is. And then give me the order of every point. So from here, it gives me the order of every point. So you can see the curve has 10 points. And you can see point 02 is of order 10. Point 05 is of order 10. This other point is not of order 10, and therefore is not a generator. This other point is not of order 10, and therefore is not a generator. But these other two are generators also, because they have the same order as the order of the curve. So I can see 4 generators. Then after that, it comes down here. Now it gives me the 4 generators. It gives me the 4 generators. So, but as I say that this is a very long code, you can customize, remove a few things. You can remove especially a point where it's giving you all the points. And again, where it's giving you the order of every point, so that it just gives you the generators straight away. Now, so this is how the code works, and we look at that. Now, so far we've been looking at elliptic curves that we just come up with ourselves, but we have elliptic curves that are cryptographically secure, those which are recommended for use if you wanted to, for example, have your data secure, like the Bitcoin elliptic curve is this. So you have so many elliptic curves that are secure. Not the ones we've been doing. The ones we've been doing are but we've been using very small p just for calculations. Is that okay? But we can learn how to calculate and so on. But now, for security reasons, we have elliptic curves that are recommended. Of course, if you go on Google and just write standard elliptic curves, and you see so many of them, they are not elliptic curves that we can exhaust in a lesson. There are so many. And they're applied in various places. Every company has its own, and it has why it has to use that. Like Bitcoin has a reason as to why it has to use this one. Zcash has its own. Even Ethereum has the elliptic curve it uses, and is not this. And again, Ethereum has reasons for that. And the major reason is about security. Is that okay? Now, so you'll go online, just write standard elliptic curves, and you will see so many of them, and that is at your own time. And the most interesting thing when you're doing that, get to know the size of A and the size of P in each of those elliptic curves. What is the size of A? What's the size of P? Like this one is for Bitcoin. Let's see what A is. This is P. This is P for this elliptic curve. How many digits are these? These are so many digits. And of course, there are not so many. They should be, I've said here, I've said that they should be a half if you're using 254 bits, then I expect that it should be a half of this. What is a half of 256? It's about 120 something digits. Is that okay? So this should be around 128 digits. But now this is the elliptic curve. This is the elliptic curve. Bitcoin's elliptic curve. What is A? A is 0. B is 7. B is 7. A is 0. You can see this is supposed to be y squared is x cubed plus ax plus b. And in this case, our A is 0 and our B is 7. And then mod the P. P is this. It's a very huge number. Now, what is even more interesting is about the order of this point, this elliptic curve, the order. How many points does it have? How many points does it have? That is about the order. And the number of points on this curve is this. This is the order. This is the order of the curve. The number of points on this curve. There are so many points. There are so many points. So if you are to use brute force and you want to try each of the points to encrypt or decrypt, then it will not be easy for you. Is that okay? There are so many points. And then okay, this one I repeated it. I repeated this, just the same as that. The number of points, the order of that curve. Now, what is the name of this? What is the name of this? The name of this curve is this. There are classes of these elliptic curves. There are classes. We are in this category. We have two classes. The category of the Bitcoin. The other secure elliptic curves that we'll be looking at maybe in future, and we look at Montgomery. It's called Montgomery. Then we have the Edwards. The Edwards elliptic curves, again, those are secure. Then we have the twisted Edwards elliptic curves. Again, we shall look at that. So while looking at those elliptic curves, our main point of interest, again, would be to see how do we add points on those elliptic curves. Slightly different from what we've already done, especially in determining the gradient, slightly different, and so on. Then from there, we'll see how do we do pairing, how do we pair a curve to another curve. Now, pairing, the concept of pairing is very much used in cryptography in terms of security. And we will try and see how that is done. Now, you remember this concept, you remember this? Why did I include this one here? This one I just included it here for you to try and see that this is an elliptic curve. What's this? This is the discriminant. We say that if it happens to be an elliptic curve, then this discriminant is not supposed to be equal to 0. So that is what I was just trying to try here. So if you take 4 raised to 3, then plus 27, and B7 squared, you get this. This is not equal to 0. It's not equal to 0. So it means, therefore, that this is an elliptic curve. Otherwise, if it will have given us 0, then it is not an elliptic curve. So this is the elliptic curve that is used by Bitcoin. So you've seen that in your choice of elliptic curves, that you must choose one that will be of higher order. Elliptic curve that has so many points, like this one of the Bitcoin. Is that okay? Yes. Should be one that has very high order. And so the other point is, for instance, if you are using 256 bits, then you require that your point should be half of that. And if you're using 512 bits, using 512 bits, then you require that your code has a half of that number of points. Is that okay? Yes. Half of that. Now, something very related to what we've been doing. How to compute large multiples of points. For instance, what I mean is this. You have point P. Are you able to get 50P? That's what I mean by computing large multiples. You'll see how this is important, of course, when you begin looking at how do you encrypt on the elliptic curve? How do you decrypt on the elliptic curve? So when you begin doing that, then you see how important it is to know how to get multiples. Given P as that, can you get a 20P? And so on. Of course, we've already looked at how to do that in our previous lessons, but I thought again, it's good to look at it in a different perspective. And we're using what I call successive doubling. Successive doubling. Of course, we had done successive multiplication earlier when you're looking at fast powering algorithm. Now, what successive doubling says is that suppose I want to compute Kp, where K is a huge number. Where K is a huge number. And so I was not thinking of the easiest way of doing that. The easiest way of doing that is, first of all, this K, I write it as binary number. So if K is 5, I'll first of all write it as a binary number. And we know how to do that. Then we'll compute 2P, 4P, 8P, up to that, depending on what I obtained here. Depending on what I obtained here, how many are there? So how many times so this one is just telling you how many times are you going to double? How many times are you going to double? That is what that binary representation is telling us. So that I know I'm supposed to get 2P, for instance, 4P, and so on, up to 50P. I want to get 50P. Then, of course, I'll see what to combine. I'll see what to combine to give me 50P. So if it was 50, first of all, the first thing I'll do, I'll convert 50 into a binary number and then proceed. This is an example. This is an example. Now, in this example, I began by the question is find the points on the elliptic curve. Just find the points first of all. Find the points on the elliptic curve. But the one that I'm talking about is this. The one that I was talking about for summation of getting, for instance, 50P, this. Show that this point has order 20, 26. has order 26. So what I want to show is that 26p is infinity, is a point at infinity. That's what I want to show. So in other words, the question is telling me, find 26p. Find 26p. So the question is, show that the point, this point has order 26 on this curve. So in other words, just find 26p and see whether the result is infinity. That's what question is saying. So for me to do that, the first thing I will do is to get 26 as a binary number. Get 26 as a binary number. That's what I did. And you remember what we were doing last time? We were considering those that have ones. Those that have ones are the ones we are considering in this summation. Of course, we do all of them, but we know we'll only be interested by, it begins on this side, ones, tens, and so on going this side. So when you're talking of 16p, 16p is this. Then this will be 8p. Then this will be 4p. Then this will be 2p. Then this will be p. So it begins, so p, 2p, 4p, 8p, 16p. But now our p is that. So using your code, you can find 2p. Using your code, you can find 4p. Using your code, you can find 8p. And then you can find 16p. But what we want is 26. So how do you arrive at 26? And it's telling us here, in fact, it's just saying that add this value, plus this value, plus this value. So add 16 plus 8, then plus 2 to get 26. And of course, when you add that, you get 26. Now, so what then happens? Use your code, therefore, to find 2p plus 8p. First of all, find the result using your code. The answer that you get, let's assume that you're getting x cubed, x3, y3. Now add this to 16p. Add that to 16p. Of course, our 16p was this. This is our 16p. So you added 2p and 8p, and you got this. Now add this to this, and see if you get the result as infinity. That's how you do successive doubling. And you can see again how binary representation was very important. And that is what makes even research easier. Research becomes easy because you only use knowledge, that previous knowledge, and see whether this previous knowledge can be extended to other areas. Is that okay? Because you can see that this knowledge was used for prime numbers, for integers. We use the same knowledge for integers when we are doing successive multiplication. And somebody comes and thinks, now, what about, can this knowledge be applied on elliptic curves to do successive doubling? Somebody comes up with that and you say it can work. So as you can do this, you can also, when you meet areas, sometimes you can also think of the knowledge that we've learned. Can it be applied here also? To come up with something that maybe somebody else would come up with. And you find that it works. Most of these things that we learn in one area, you find that they apply in another area. That is why you find when you're talking about encryption to do with numbers, those scheme, somebody again thinks of that scheme, how do I do this scheme now on elliptic curves? And you find it's the same scheme. The same scheme, only that this time is now using points on the elliptic curve, but the way they work is just the same. And when you go to lattices again, you think of how can this scheme again be applied here. And you find it will just be the same scheme, but now applied again on points on lattices. And even the signatures, the schemes of the signatures and the protocols, you find that they are always the same. It's only that it's applied in a different environment. So that's why you need to know, for instance, how do you add points on the elliptic curves? How do you double points? Then after that, borrow the knowledge of how you did with the integers when you are doing those schemes, and now use the same knowledge now that you know how to add and do and so on. That is what usually happens. So this knowledge, you can always apply it. Always applied in new areas. Now, this is the same example. This is just the same example. I want to find 13R. I'm given R, then I want to get 13R. So the first thing I would then do, I would convert 13R, write it as a binary number. And so I will then get R, then double it, then get 4R, then get 8R. And it's telling me, of course, if I double it again, it will be 16, and 16 is beyond what I want. So I stop at this. I cannot double it again to get 16. 16 is beyond what I want. And what it's telling us, that you'll add 8. That's what it's telling us. You add 8 plus 4. 8 plus 4, and then plus 1. 8, 4, 1. 8, 4, that is 12, then plus 1, that is 13. And so you use the code to do that. Use your code to do that. Use your code to find 8R, for instance, and then find 4R. Then 8R plus 4R. Then again do that result plus R. You have 13R. 13R. Now, I had not included the code for doing that here, but I have it. The code for doing successive doubling. Yes, I have the code for doing successive doubling. Just open it. Now, it's code of successive doubling. Now, so this is the code for successive doubling. Now, the code I only require A, so I deleted B. I deleted B, but I'm doing it mode 19. Then this is the point that I want to add it a several number of times. Now, so what I've done is for I in the range of 1 and 10, for I in the range of 1 and 10, I want it to give me 1 multiplied by this number, 2 2 multiplied by that number, and so on. So let me see what it then does. Yes, I wanted to double it up to I is 9. So it's giving me 1 multiplied by that number, of course, then 2. Okay, the first doubling, then now when you double this result, this is what you get. When you double this result, this is what you get, and so on, and so on. So, but what you can do now, this code, you can now improve on it. And this time, instead of asking it to do double in a given range, you can just write something that you can ask it to give you 30p, and it gives you 30p. Is that okay? You can ask it to give you 29p. For me, if I wanted 29p, you see, I cannot do this code. I have to ask it to do for me the range of 1 to 30. Then I'll myself pick out what 29p is. So if I ask it to give me to do all double everything up to 30, up to 29. Then so that now I just pick out what is 29p. But you can now be try to customize so that you just tell it what you want. You see, for me, if I wanted 29p, I come and pick it here. If I wanted 26p, I come and pick it here, and so on. If I wanted 24p, I come and pick it here. So I've told it, and you see, when you give it a lot of work, then it becomes slow. But if you give it less work, faster. That's why I say you can now customize and just ask for it to give you, for instance, 43p. It does that. Thank you. That's what I wanted to share today.